would like to thank the professors and researchers for preparing this great workshop. And today, I talk about the unique and abrupt CO2 uptake change in the South Polar North Atlantic region under the global warming. As you know that the oceans are absorbing much of the anthropogenic CO2, about 30% caused by the climate change. And then the observed anthropogenic CO2 is stored in the ocean as the dissolved inorganic carbon. And under the global warming, our system models project that the global ocean carbon uptake would exhibit a relatively linear response to the rising atmospheric CO2. And among the ocean basins, the North Atlantic Ocean is the one of the most effective reason to absorb the anthropogenic CO2 and store the CO2. However, according to the previous studies, the future North Atlantic Ocean carbon uptake cannot simply explained by the linearity. Under the future climate scenarios, AVAC is expected to slow down and permanent collapse in a long-term time scale. And also, the dynamic CO2 sequestration and North Atlantic carbon storage is also weakened. Also, most of the current studies are limited to simply understanding the North Atlantic carbon cycle only by reflecting the AVAC response. At the same time, the collapse of the AVAC should not be treated identical to collapse of the Labrador Omega sea mixed layer, footprint of the deep convection, and also the South Polar gyre. So the SPG or the deep convection is strongly coupled with the regional carbon cycle, and this implies that the possibility of losing CO2 uptake ability over a much shorter time scale. So in this study, we investigate how local dynamic changes the SPNA carbon uptake under the warming scenarios. This is the data that we used in this study. So in our lab, we ran the 3 different speed emission-driven experiments using the CSM2. So this is the experiment design and the experiment name. So based on the SSB 585, we refer to the ER1. We integrated ER 1.5, which is 1.5 times the emission rate of the ER1. And also the ER 0.5 is conducted with half of the ER1 emission rate. And also in the case of the ER 0.5, we ran more additionally the 15 years to simulate the substitutionary global warming. And this is the result of the atmospheric CO2 concentration. So all of the 3 experiments, the CO2 concentration increased exponentially. And also, we ran 7 ensemble, and I used the annual mean result. So this is the result of the ocean CO2 uptake. So first, this is the special pattern of the LC CO2 flux changes last 10 years. And we can see that most of the whole ocean basin keep uptake the atmospheric oceans. The blue, the minus sign is referred to the sink, CO2 sink. And also the SPNA region, however, is becoming less observing compared to the other ocean basins. And also we check the area integrity time evolution, the global, tropics, and southern ocean. And you can see that most of the ocean basins, the CO2 uptake continues to the strength over time. And as I mentioned before, in the case of the SPNA regions, interestingly, we think that the pronounces the special patterns in the SPNA, we really think they closer resemble to the Atlantic warming hole. So we named it here as the CO2 uptake hole, where the anomalous outcasting of the CO2 flux is stronger. And when we see the area integrity, the time evolution in the SPNA region, we can see that there's an abrupt rebound time in all the experiments. And this means this time evolution means that the CO2 uptake becomes weaker after each rebound time. And this green line refers to the synthetic temp models, and according to there is some uncertainty in each models, but when we see the multi-model mean, the features is really similar to our experiment. So we focus on and analyze how that kind of the CO2 uptake hold is happened. The air CO2 flux is determined by the environment factors and also the difference between the partial pressure, ocean, and atmosphere. And also you can see that this is the difference of CO2 partial pressure features, and air CO2 flux is mostly proportional to the dpCO2. And when we check our experiment, the atmospheric pCO2 is not different from the spatial distribution. So we think that the dpCO2 can be determined by the ocean pCO2. And also the ocean pCO2 can be decomposed by that kind of the environment factors, SSD, DIC, alkalinity, and also the freshwater tones. And also, that is to comprehend the air CO2 flux is need to understand what driver leads to the ocean pCO2 changes. So this is the result of the ocean pCO2 decomposition. So consistent with the previous studies, we can see that the DIC, the green line, is the main driver to increasing the ocean pCO2 in most of the basin. And the other factors, like the SST or alkalinity or freshwater tone, is the minor contribution to increase the ocean pCO2 change. However, interesting thing is that in the SPNA region, the DIC contribution only exceeds the total, the black line, the total ocean pCO2 changes related to the other ocean basins. So to examine the distinct SPNA CO2 uptake changes, we analyze the regional deviation from the global mean. So when we check the regional deviation of the SPNA, compared to the global mean, the DIC is highly contribute to increase the ocean pCO2 changes really rapidly in the SPNA regions. And also the DIC contributions are accelerated around the rebound time. This is the vertical line. When we refer to the front of the air CO2 flux in the SPNA regions. So around the rebound time, it also coincides the notable increase of the ocean pCO2 changes. So that is that abrupt increase of the surface DIC in the SPNA region increases the ocean pCO2 higher, and that makes the CO2 uptake weakening. So next, we analyze the physical feedback what physical feedback making that kind of the really fast, rapid DIC accumulation. So when we listen to about the SPNA region, we can easily think that the first candidate of the physical process is the AMAP. But according to the previous study, the reduced AMAP and its meridional transport could be contribute to the DIC accumulation in SPNA region because DIC pool water in the subtropics less transported. But when we see the AMAP time series, it is a little bit hard to think that the gradual slowdown of the AMAP weakening is main causes of the abrupt increasing of the DIC accumulation. So we think that there is the other really more direct process to determine the nonlinear CO2 uptake. So around the SPNA region, there is one of the most ocean where the deconvection is observed in around the Labrador and Ominga Sea regions. Also, when you see the DIC, climatologically DIC vertical profile, the DIC concentration is much higher rather than the higher concentration rather than the upper ocean. However, when we check the deconvection, the mixed layer around the Ominga Sea, this is the black line, the deconvection is declined, and suddenly it collapsed in all three experiments. And this collapse time makes the de-ice accumulation as soon as really faster after the mixed layer is collapsed. Also, it is sure that the timing of the mixed layer collapse timing is really similar to the LC-CO2 flux rebound timing. So, therefore, we figured out that the mixed layer collapse significantly acts as the positive feedback to amplifying the surface de-ice accumulation. And so far, we focused on the temporal evolution in terms of the multimodal mean. So we compare the AMOC strengths between when the LC-CO2 flux rebound and when the mixed layer shut down. And there is a strong linear relationship between the kind of the timing of AMOC strengths. So according to this linearity, we want to say that the reasonable deconvection can be more direct modulator to CO2 capacity in this region. So this is the last page. So finally, I conclude my presentation with sending the implication of this research. So interestingly, the SPNA CO2 flux and also the AMOC and mixed layer and DIC have the nonlinear relationship regardless of the CO2 emission rate and also the model configuration. So this is the important point because despite those Atlantic is a really complex environment reason, but the uptake hole is a really robust phenomenon in here. Also, according to the compare with the observation and also the reanalysis data, this is the vertical gray line, and also the threshold line, we can think that there is the relatively little room for the approaching the CO2 uptake hole. So we want to emphasize that this finding could be the potential indicators for understanding the prediction and more accurate future those Atlantic carbon cycle dynamics. And also, we can warn about the emergence of the CO2 uptake hole might be a little bit difficult to avoid. Thank you.